I'm Alan Marshall. I'm a professor of chemistry and biochemistry at Florida State University. My grandmother used to send me out in the yard with a magnet, and I'd go through the dirt and pick up iron filings for her to use for fertilizer. Coming out of high school, I went to Northwestern because that was had just started a 6-year med program. So the idea was to go 2 years to undergraduate and then 4 years to med school. So I went through 3 years of that, and I discovered that I liked medicine, but I hated medical school. And so the only degree I could get in the remaining year was chemistry. So that's how I became a chemist. And then went on to graduate school in physical chemistry, and now I'm called analytical, but it's basically physical chemistry. When the decision came down to move it to Florida, I called up the director because MIT was never interested in the cyclotron. And so the director took a chance and was willing to hire me and build up the program. So really, we owe it all to Jack Crow, the guy who founded the Magnet Lab. And Florida State has put a big investment in as well. So inventions, most things aren't truly invented. They're just borrowed from one area. So mostly people take something that's well known in one field and apply it to another. So that's what I did. I knew about Fourier transforms from NMR and thought maybe we should try that for this other experiment. Yeah, the cyclotron says that when you put a charged particle in a magnetic field, it rotates around the field. And it goes at a rotation frequency that tells you the mass. And so that's what we use it for. We basically weigh molecules. And when we weigh them, accurately enough, we can tell all the atoms that are in there, how many carbons, hydrogen, oxygen, sulfur, and so on. You need that accuracy to be able to tell things apart and also to be able to identify what it is. Fourier transform is basically a mathematical tool, so it converts integrals into multiplication and division, so it makes the math easier. And what it does for us is it gives, as I said, gives the whole spectrum at once instead of one at a time. At the beginning it was such an effort to get this spectrum, 1,000 data points to get one peak, that I had to write down all the data points by hand and then type them onto paper tape, feed that into the computer, and then eventually get the Fourier transform. So all of that took about a day and a half. Now it takes a second. Well, the first sample was methane, basically natural gas, and one peak because there was just one compound. And when we sent that to the journal, they rejected it. They said it didn't really look like it was going to amount to anything. And so we eventually did get it into another journal, and it's been cited 1,000 times. So that was fun. And over the years, the number of peaks just kept getting bigger. I think the most obvious one is the Gulf oil spill. When that happened about 5 years ago, we got samples of the oil and we analyzed them, and we found that we could identify the oil and know that it came from that spill rather than somewhere else. So I moved here and I left all of our existing equipment behind, so that would force us to build everything from scratch. So our first instrument was 9.4 Tesla, that's 94,000 Gauss. And then gradually we built up about, over the years we got a second one of the same field, and then about 10 years later we got 15 Tesla, and then last year we opened up a 21 Tesla magnet. So there are 4 main instruments, but it's a continuing evolution. It's not just the magnet, it's all the other stuff that goes into the spectrometer that's really made it pay off. When we did it, there were about 40 people in the world doing the experiment in very specialized physical chemistry. And what happened later is it became possible to do the experiment on biological molecules and things that were of very high practical interest. So none of that really we foresaw at the beginning. So you never quite know what's going to be around the next corner.